Okay. Okay, if you're not here, raise your hand. Oh. Okay. My name's Bruce Faraday, KF70ZK, Vice President of the Utah Amateur Radio Club, and we welcome you to our meeting in our different classroom because, hey, we had to work out the technological issues that were beyond our ability to deal with over there. All right. Do we have any new hams or new to the club here tonight? We got one. All right. It gives your name and call sign.
I'm Brent Meller, KM7FIV.
How long you been ham?
2 weeks.
All right.
Thank you. Just a technician for now, but I'm going for a general.
Good. Good luck.
Within his 2 weeks in the hobby, also go ahead and talk about him and compliment him on how he saved us with the AV equipment here.
Yeah, he's helped us get moved over to a room that actually allows us to have the microphone and the camera working and everything. So we appreciate your help.
Thank you.
All right. Huh? You're new here? No?
Yeah.
Stand, your name and call sign.
Okay, my name's Rick, KM7AIF. I joined this club about 2 or 3 weeks ago, so I paid my dues. I should be eligible. Anyway, I started out the club at the Crossroads last fall because I gave up on ham last year. 2 meters, nothing, crickets, and I just put my radio away until I thought, God, I'm going to join a group. So I joined the group here first, and the rest is history. Now I can't get away from it.
All right, and upgrades. Anybody upgrading or have upgraded? Sylvia, that's right. Okay, Sylvia, tell us what you got.
I just upgraded to extra, and I'm in the process of applying for my late father's call sign, vanity call. So carry on.
All right, way to go. And I know she put a lot of effort in because I helped her out in one test session. She went through 3 tests and just barely didn't make it. And she went and took it again at another place and was able to pass. And I think that's just wonderful. So. All right. Okay, now. Oh, that's up there already. Rick, tell us what you got in books. Anything new, anything special? So.
Yeah, Bruce got a little extra exercise. We are restocked in the using the Baofeng radio. Also restocked with Parks on the Air. And brand new satellite operating for amateur radio. And almost as new, digital networking for ham radio. Why one says ham and one says amateur, I have no idea. Anyway, we still have caps if you want to keep the sun out of your eyes.
All right, way to go. Yeah, I was out at the Salt Flats 100 endurance run, and they were using All-Star Link to connect everybody up with digital and everything else. It's got fun. So, an All-Star Link is similar to Starlink, but not the same. So, don't need to grind the chalk into the ground. All right. Yeah, and speaking of the service possibilities of amateur radio, you can go to utah-threat.org, and they have a lot of the calendars of the different events and who to contact to get into that. That'll get you into the marathons, into the runs. I know that they had a couple of 100-mile deals, one in April and a couple in May. One last week out in Twilla. Week before that out by Wendover. And it gets fun, especially when you run into the need to help somebody not die out there. And there was a couple of opportunities there. We had call ambulances or we're waiting on people that were just spent, and they had to get some race crew out there to go pick them up and take care of them, because you don't want to spend the night out on the salt flats. And I'll write it up on the board. There was one about SAG, Utah SAG. That's defunct, no longer functioning, and it's all moved over to that. I do know that there's a couple of marathons in July, Deseret News Marathon, the Pioneer Days Parade, and they use amateur radios to keep track of who's doing what and where, and if somebody's needed help for that, for those kind of things. There's also one it's the weekend after Labor Day. It's the Wasatch 100, and that's a 100-mile race up over the mountaintops, Layton to Heber. And yeah, people can get in trouble on that one too. But more important, the fun one, Field Day, Payson Lakes. Same place as before, June 26th through the 28th. You can come up there on any time from the 23rd, and it's a fun place to hang out, bring kids, go camping, go fishing, get away from everything. Usually.
If you got a moment, I'd love to talk about it.
All right.
Go ahead, James. Yeah, so this is James, KK7AVS. Currently this year, I ended up getting roped into it, or I voluntold myself to do it. I'm a Field Day chair this year, so I am really excited about that. So we just barely have enough activity or volunteers to where we might be able to pull this off. So we're still going to be at Payson Lakes, which is going to be really neat and really awesome. That weekend, a little bit before, free camping spot, ham radio for the day, 2 large towers, beam antennas, 2 dipoles, a lot of radios, and a lot of people in the hobby too. And it's going to be a lot of fun, and it's going to be a really great weekend. I sent you all an email out asking for volunteers to help out with Field Day. Logistics, setting up at Field Day, some of the technical aspects, and what you might want to learn, what you might want to gain from Field Day, or what your interest might be. But I only have 2 volunteers currently assigned that have volunteered to help me out with Field Day. So it's the board here, it's me, and it's 2 other people. But I sent everybody out an email to sign up if you want to volunteer for Field Day. We're going to have the sign-up sheet on the main page of the UARC website here shortly in preparation for the next meeting. But yeah, look for that scrap email, or shoot me an email at kk7avs@gmail.com if you have any interest in Field Day and what you might want to take away from it, or what you might want to learn, because we're interested in having you help with any part of the setup process. And yeah, we just want to make everybody's Field Day a great experience for sure. Yeah, for sure.
I don't understand all that. So you get together out in the field and talk on your units? Is that what you do?
Yeah, for sure. Go ahead, Bruce.
Next month's meeting is all about Field Day. And yeah, we go up in the mountains and operate as if we are in a no power, no communication situation, talking to as many contacts as we can make in a 24-hour period. And we usually do pretty good. Okay, we have 2 towers with beam antennas on top. They're tri-bander beams. One is an 80-foot tower, and it's mounted on. They're both mounted on trailers. We have power supply generator, propane powered, that we can have all the power we need for up there and to run all the equipment that we have. The hard part is we need to get the towers up the mountain. So right now we're looking for at least one 3/4 ton or better truck to be able to move them. The towers right now are in Payson Canyon, but they need to be taken up the top. And one of them needs to be taken down and fill the propane tank and then taken back up. The campground is about 12.5 miles up the canyon, and it's about 25 to 30 mile an hour canyon. So it takes a while to get up there. And of course it's a windy road, which is kind of why we need the heavier truck and that. The tower, the 80-foot tower, that trailer's over 10,000 pounds.
Between the 2 volunteers we have currently, logistics is covered.
Okay, so that's covered. The other one is we have a shed here in the valley that contains a large quantity of radio gear that we use for field day. And I have seen, in the years past, we've packed maybe 3 or 4 cars or trailers with this gear. It includes radios, antenna gear, coax. It's two level pickup truck loads, yeah. It's all boxed up so that it's contained in that. So, but we just need to get it up there. We also, on Saturday, we have a potluck dinner during the field day event. And I think I've been volunteered again to cook. Yep. I think Noji says something about that, right?
Yes, we volunteered. Yes.
Voluntold. I think I got in trouble the year I didn't show up, right? Yeah. Yeah, that was 2 years ago. I could not get out of something like that. So, yeah, they go do something simple when I'm not there. Then, any questions on that? Jerry, did you have something?
I have something on field day, and then I have an
Announcement. Oh.
So one of the larger clubs along the Wasatch Front is the Davis Club. Davis is not doing field day this year because their board said, why are we doing field day when it's just the board who shows up and does all the work? And I really can't blame them for that. So we do need people to step up for field day on an ongoing basis if we're going to be able to continue doing field day. So that's my grumble. But the announcement I have is September 11th. Thanks, James, for throwing me under the bus. The Civil Air Patrol has reached out to the club, and they want to put together a radio telescope demonstration, and James was kind enough to tell them, oh, Jerry does that. And so some of you that might want to be involved in another aspect of amateur radio and radio telescope, right now we're scoping out the project, but there's a good chance that we're going to do a hydrogen line experiment, which happens to fall in the 20-meter band, by the way. And from that, we can do things like measure the size of the Milky Way and other stuff like that. And so if you're interested in that, reach out to me. I can be reached at Brummett@X Mission. My email is in the microvolt, so go find it in the microvolt. Another good reason to go see this month's microvolt. So if anyone's interested in radio, telescope, and Dalen, you're here. I want to dragoon you for this project. So, yeah, I want to volunteer Dalen to help me with this.
Okay. So field day's a lot of fun. The thing with amateur radio is get involved. Go out and do these things. Get out. I mean, at least with field day, you get out in the mountains and enjoy just not being in town. And also we're at like 9,000 feet, so it's a little cooler. Yes?
What's the rough schedule of field day? Like what's done on Friday, Saturday?
Okay. Rough schedule on field day. Real simple.
You want me to do the spiel? I still haven't memorized.
All right, go ahead.
So real quick, Field Day overall is the largest ham radio event in the States. It is Canada and the US. It's 24 hours on the air. We make as many contacts as we can. Thank you, James. You make as many contacts as you can. Every state is broken up into localities. You're trying to get as many contacts and trying to get the whole country if you possibly can, including Canada. So we can set up 24 hours ahead of time. James, have they continued the extension? Is it still at 30 hours?
Yes.
Okay, so it's 30 hours. So Friday, starting at 8 a.m., we'll start setting up our towers. They're 2 large trailers with crank-up towers. We'll start setting up our tents and our stations. Then starting at noon on Saturday, thank you, we will start transmitting. We will be on the air for that full 24 hours as much as possible. Sorry to step on you, Bruce, but the last 3 years, I've been the field day coordinator. We will run overnight. The overnight shift is the best shift. Usually I show up with coffee and some sort of pastry. You can hammer out contacts. My first field day, I did over 600 contacts. You can really and truly get your practice working a pile-up, working HF, and as long as you have a control operator with you, you can work the full band. You do still need that control operator and their privileges, just like you're transmitting anywhere else. So 5:30 or 6:30 on Saturday, we'll have the 5:30, thank you. 5:30 on Saturday, we'll have the potluck. The club does provide a protein. Aside from that, please bring a side. And do we have a sign-up sheet for that?
We do.
Thank you. We have a sign-up sheet because we have on multiple occasions had nothing but cookies. Please sign up if you're going to come to the potluck and let us know what you're bringing. Look what other people are bringing. Don't everybody bring cookies. We all love sweets, but you got to have more than sweets. Then Sunday at noon, we will start tearing down everything. Usually we can do it in about an hour and a half. Yeah. Hour and a half, 2 hours. Yeah, it takes much longer to set it up than to tear it down. And we always need help on Sunday. Sunday is always the leanest crew. Everybody's happy to set up. Please sign up for takedown as well if you're available on Sunday. What did I miss? Did I answer your questions on what field day is?
I can usually have enough protein left over for a lunch on Sunday after it's all broken down. So it's
some sort of snack.
Yeah.
And sorry to introduce myself. My name is Adam Stribling, KK7NJJ. I am the president of UARC. These folks were bright enough to vote me in. What can I say? Any other questions about field day before we move on? Scott?
Just a comment. If you want radio time, you will have plenty of radio time. Sideband, CW.
Yep.
Take it over.
As Scott mentioned, if you want practice on the air, we have amazing folks that have years of experience that are true contesters that will be there. They will teach you and help you use your voice better to be heard better. There's a lot of techniques that aren't as straightforward and simple as you think. It's an amazing experience to be able to get on the air, have somebody helping you, and really and truly knock the dust off of your skills or grow new skills. And as Scott said, we will be running CW and sideband. Are we planning on digital this year, James?
Yeah, if somebody wants to bring some equipment to do digital.
I should be able to lend you my 710 with a laptop set up, so we should be able to do digital as well.
Yeah, we'll still the CW10.
Okay. So yeah, we're planning to run digital as well, probably just FT8. Jerry, question, comment?
So one of the other things is if you're having trouble doing anything in your shack, anything in amateur radio, want to talk about electronics, come up and camp, sitting around the fire with some of the smartest people in electronics and ham radio in the Intermountain West come to our field day. And you will learn so much. And so if you're a technician wanting to go to general, if you're general wanting to go to extra, if you want to talk about how propagation works and things like that, finding somebody in a meeting or when we're doing something, but in the evenings at field day, setting up, those sorts of things.
Yeah.
That's a real good way to spend your weekend.
Let me take that and run. So what Jerry commented, sorry, I didn't run the microphone over for those of you online. Field Day is the place to meet an amazing Elmer, to just gain contacts within ham radio. All of us have our niche within the hobby. One of the beautiful things is that it's an amazingly broad and deep hobby. We'll have guys, if you're having trouble with your equipment in your QTH and your home station, come ask questions. We'll be sitting around the fire, we'll be operating, and you'll gain an amazing amount of experience. You can get your questions answered, and the other great place to come and meet people for finding an Elmer or finding somebody that has ran into that one weird problem you have, like COM ports for digital, you can meet them here at a meeting. In person, QSOs are the best. Not that we don't all love being on the air. Did I cover most of that? Thank you very much. Any other questions, comments about Field Day before we move on? And I don't know if you covered it, but our next meeting, our June meeting will be all about Field Day. Please come if you want to attend Field Day, and you can have all of your questions answered right then and there. Bruce?
Okay. Thank you, Adam. And if you want to volunteer to help, get in touch with James or any of the club officers, and we'll help you get involved. Next one is steak fry. And steak fry is $15 per person. It includes the steak, potato, corn on the cob, salad, dessert, and it's going to be held this year at Murray Park. We've previously had it up Big Cottonwood Canyon, and between construction in the canyon and a facility that is deteriorated to the point where it's unusable, we decided to move it. So it's going to be there in Murray Park at Pavilion 1. You'll find the address and instructions on the website. Do we have any classes this? It's on the 18th, Saturday the 18th. Do we have any classes?
Well, I have nothing scheduled for classes. I do teach technician classes over Zoom, and I do teach general classes over the air. So I usually start those every quarter, but I haven't started them recently. We're running a few weeks behind. I need some students. So if you know anybody that wants to upgrade from technician to general, or somebody that needs their technician license, have them shoot me an email at kk7avs@gmail.com, and we'll go ahead and get the ball rolling.
All right, thanks. Our last one is trailers. I need a parking spot for 2 trailers. Right now they're in the canyon, in Payson Canyon, a Boy Scout camp, and we would like them a little bit closer, because if we want to use them here in the valley for something other than field day, it's a haul and a half to go get them. And if you want it for winter field day, they're inaccessible because of snow. And that's one of the things we're planning on this year, winter field day here in this valley. We did it this last January. Turned out, and it turned out pretty good, except we were limited for time because of the site didn't let us go past 9 o'clock at night. But we found other sites that don't have that restriction, and we would like to be able to throw up some, be able to go down there and set it up and run it. All right. Now we're going to have a presentation that's going to be a little bit, well, I was going to say shocking with a little pressure involved. But we have a special presentation from Sabra. Did you have something to say?
Oh, me?
Yeah.
Yes, I was going to say that there are at least 5 people, I think, who didn't get any tickets.
Oh, did everybody get a ticket for the drawing?
I didn't.
Oh, you got it filled out.
No one ever told me mine was.
Okay. We got you taken care of. If you don't have a ticket, raise your hand and they'll get you one. Okay, so we have the crazy Professor Noji, who's going to talk to us about piezoelectrics. And I assume that most of us know what a piezoelectric crystal is. I'm going to let him take care of it and give us the presentation. Go ahead, Noji.
Thanks, Bruce. Is my lapel mic on?
Yes, sir.
Okay, good. Because I have a soft voice, and so I asked for a lapel mic, so in case my voice doesn't carry very well. But anyway, thanks to everybody who set up and all that good stuff. I am not a professor, just so you know. My brother is a professor. My brother Al, yeah.
You're professing what you know. Did you play one on TV?
That's right. I play one on TV, and I'm professing that I'm not a professor. I'm just going to pull out a few toys, if you don't mind. I get bored easily, so I just got to play with toys as I'm talking. Is that okay?
You want a table brought over?
Yeah, we can bring that. Here, James, I'll give you a hand.
Oh, a table?
Yep.
Oh, thank you. No.
Here you go, Noji. Right.
Thank you so much, you guys. What would I do without you? Appreciate it, Adam, James. Well, this is my only slide, just so you know. My name is Noji, and it just came and went. So I'm going to press.
Whenever you're ready.
I'm ready. Thank you very much. There you go. Any questions? Okay. I told you it would be quick, okay? I didn't say it would be good. At any rate, so we're just going to talk a little bit about crystal oscillators, and people might be wondering, why the heck would we even talk about that? And, Rick is going, what has that got to do with my life? Your life might be changed tonight because of this very discussion. But then again, it might not be. So let me just kind of dive into this and kind of explain what's going on. If we can just, because I'm just going to go through this really quickly. Sorry. James is doing his very best to follow me, and I'm just not giving good clues. At any rate, I just want to talk quickly about vibrations. And vibrations are kind of what we are starting with talking about this. As a matter of fact, I went and picked up this little tuning fork. Some of you might recognize this, but this is an official 440 hertz tuning fork. And what that means for those of you who are musically inclined, that's an A. Okay, and so if I can do this, I'm not sure if it'll work or not. I'll hit the tuning fork. Oh, there's the microphone. There we go. Try again. You can hear that A sound, huh? Okay. So what that is a mechanical vibration. So that little tuning fork actually produced a mechanical vibration in the air, and you can hear it, and you can even feel it. In fact, I can feel it really good on my teeth. So tuning fork, great. And what that does is when it produces that mechanical vibration, it moves the molecules in the air, and that produces sound, among other things. Tonight, what I want to do is distract you away from that tuning fork and talk about an oscillator. An oscillator is a piece of machinery that's dear to our hearts, those of us who are ham radio operators. And we depend on oscillators. Oscillator is something that's not sound and not mechanical, but it's electrical. And as a matter of fact, it uses AC current. In fact, it makes AC current. And alternating current means that the current is going in both directions, positive and negative, back and forth all the time. And that's what that's for. And this is what we need to make radio signals. Without AC, there would be no radio. Simple as that. So that means we need to have an oscillator to do that radio stuff that we do. Well, a long time ago, they decided to create an oscillator. Well, they first did it with mechanical means. Tuning forks did not make good ham radios, so they turned to a thing called an LC oscillator, and that was comprised of a capacitor and an inductor. So this diagram you're seeing is an animation that shows a capacitor on one side and an inductor on the other side, and when current's flowing, it actually will flow back and forth between the two. And because it looks like a kind of a tank full of liquid that's sloshing back and forth, this is actually called a tank circuit because of that visual. So this little guy here is an oscillator because it creates this oscillation going back and forth. I'm not going to go into any detail as to why this does this. That is saved for another discussion. In fact, we had that about 1.5 years ago, of why an LC oscillation occurs because of impedance. So here, I will go through some rudiments. So even if you apply a small amount of energy to this tank circuit, it starts going right away. Current starts flowing back and forth between them. And often they used to call it a tank circuit, and that's what we are using now. Well, kind of. The thing is that since we use it for tuning so much, we have depended on this tank circuit to actually create one particular frequency or to receive a particular frequency. But there is a problem with an LC tank circuit. Well, there's many. I'm not going to go through all of them, but there's one particular problem that's, again, kind of dear to our hearts. And one of them is that, well, it's because of temperature. Anyway, let me just explain, first of all, the resonant frequency of the LC oscillator is calculated from this. Just so you kind of get in the background, I'm not trying to hide a bunch of things by numbers, but I'm just trying to show you where this comes from so we can talk apples and apples. So this comes from the equation for impedance, Z equals R plus JX. And JX is just simply reactance. Reactance is an interaction between capacitance and inductance. And in this case here, the reactance is the difference between the inductive reactance and the capacitive reactance. Now, resonance is defined when X, that reactance is 0. Only way to make X 0 is if both X sub L and X sub R or X sub C are equal to each other. So we just happen to know that X sub L equals 2 pi FL, L being the inductance and F is the frequency. X sub C, the capacitive reactance, is 1 over 2 pi FC. Okay, still bear with me. This is the only slide you're going to have to bear any equations. But when we set these equal to each other, then we have this relationship here. What we're trying to do is solve for frequency. We want to know what frequency are these two in a tank circuit oscillating. Well, solve for F and go through all this, and you get F equals 1 over 2 pi square root of LC. So there you go. That's how you calculate the resonant frequency of an LC oscillator. Simple as that. Okay, in real life, not quite so simple, but we're not going to go into any of that detail. This is basically how it works. Now, taking that very same thing, the frequency calculation from the LC oscillator, if I, for instance, have a capacitor that's of 12 picofarads, and I find that my inductor happens to be 40.7 microhenries, okay? Rick is going, who cares? Why are you talking about this? Bear with me. Eric says, I have no clue. Is that what you just said?
No,
he says, I have no clue. So, thank you, Rick. I appreciate your intelligence. I'm going to bring you up here.
No, you're not.
Yes, I am.
No.
I need someone to help me demonstrate this. Okay, so Rick says yes. You got it on camera. So if we calculated that, the F turns out to be 7.202 megahertz. pretty convenient for those of us who are ham radio operators operating on 40 meters. But the biggest problem that we run into is known as drift. And so what happens is, if the inductor starts warming up, how would the inductor warm up? What would warm it up?
The reactance, the resistance.
So the simple resistance of the inductor itself, right? The current going through it, is that what you're getting to?
That and ambient temperature, maybe.
The room temperature even, yeah, it can warm up that thing. What else can change the temperature of an inductor? I mean, here's Rick. He's operating his radio, this LC oscillator, and he breathes on it. Well, can that warm it up too? Of course it can. Anything can, okay? His cat that's laying on his rig, that's warming it up. So anything that changes the temperature, and in fact, if you change it by 0.2%, what's a good tolerance level for these components? 10%, 20%, even if it's 1%, okay? If that tolerance, we have already violated it by going to 0.2% with a change of 40.8 microhenries. And that's what? 0.1 microhenry. That's 100, nanohenries. Holy cow. Just because you've breathed on the thing wrong. And because of that, you've drifted that far away, 9 kilohertz, and suddenly your contact can no longer hear you. That was a problem. Well, it kind of still is here and there, but you know what? There came some really important and smart people that actually solved this problem. So because of temperature stability, so now there came engineers that came along and said, you know what, we can help a lot by changing the material that we can make these things out of. Okay, that helped a lot, but it only went so far. Eventually, there's a really smart guy named Edwin Armstrong. He came along in 1913 and said, I can probably figure this out by making a feedback loop in a circuit. And he did it with some tubes. He went down to Radio Shack, brought some tubes, put it together and says, look, pew, we got this thing down now where this thing is staying within 1%. Really good. Not good enough for us amateurs, but it went really far. Still, the circuits he made, and by the way, there are two schematics on the diagram. The one on the lower left is a Colpitts oscillator, the one on the right is a Pierce oscillator. And he made these, not these very ones, but like these circuits in order to stabilize the oscillator's frequency. And it went really well. They were a little expensive. To put those into everyday ham radio operation, you had to go buy the tube, you got to go buy the socket, you got to buy all kinds of things. And Rick's going, oh my gosh, that's so frustrating because I want to get this thing right, but I keep wanting to talk to Jerry, but she goes away and I keep having to turn the tuning knob. Anyway, and suddenly field day falls down in its face. So sad. So once upon a time, there were two other guys that were also very smart. And they came up with an idea through some experimentation. And they said, you know what? We know that you can actually come up with some vibrations and oscillations differently than what we're doing right now. What they actually figured out was that they can generate electricity from crystals. Well, that's kind of weird, don't you think, Rick? No. Rick says, yeah, that's weird. He and I are like brothers of another mother, okay? We just agree on so many things. Well, what they found out was that actually crystals had some special properties to them, one of which was that you can actually generate electricity. It's like, that's odd, crystals. In fact, I happen to have brought with me here a crystal. This is a quartz crystal. It's very pretty. It looks like glass, feels like, does it smell like glass? Rick says it smells like glass. And so it must be glass, but it's not. In fact, it has a very different crystalline structure than glass. Glass is not a crystalline structure material. You cannot make a crystal out of it. But this thing here, I can almost kiss it. It's so nice. It's so perfect. You can slice it up and make radios out of it. Anyway, so very nice crystal here. And this kind of a crystal can actually generate electricity. I'll prove it to you. Rick says, no way. I don't believe it. Well, anyway, so let's see. Down in the lower right of the slide here is a picture of of a bunch of purple crystals. It's kind of rare because it's so nice, and they're really, there's like a whole bunch all up together, right? A bunch of teenagers haven't come along yet and just smashed them. So this is really nice looking crystal, kind of like what this one is here, only purpler. But anyway, it's kind of the crystal that they actually used to discover something very strange. And now let me just, before we go on, let me just explain to you what voltage means. And this is where these two guys came in to kind of help us out. When I say voltage, I'm talking about an electrical potential difference. So if one thing has a potential and another thing has a different potential electrically, that's called voltage, the difference between the two. Okay. Now, if you look at the picture here on the upper left, you're seeing 2 point charges. And these two charges, one's positive, one's negative. It doesn't have to be a point. It doesn't have to be an electron or proton or anything like that. It could be something like an ion, for instance, anything that's positively or negatively charged. And when you have those two different charges, you have a field between those two, and that field is called the electric field. Now, this electric field has potential, and it can be seen from the outside of these two if the potential difference is non-zero, especially. And so if one charge was greater than another, then suddenly you have a potential difference. And so the electric field has a non-zero voltage. That's kind of how he's, and for you purists, and so I'm glossing over a bunch of things. I apologize. I know that I am. Forgive me. Too bad. Okay, so on the right, by the way, is my good friend Reddy Kilowatt. In fact, I was going to ask if anybody knows his name, but none of you guys are old enough to know him. So anyway, that's Reddy Kilowatt. What's your name?
Bob.
Bob says he does. Do you know Reddy personally?
No.
He says yes, he does. He's that old, and I believe you, Bob. So, and he's just a good friend there to help support this theory about electric potential. Now, the result of the electric field potential differences are what we're after, okay? The balanced ionic charges, like in a piece of glass, even in this crystal right here, this crystal, this quartz crystal, the charges in it are completely balanced. There is no, I mean, you can hook up a battery to this or a light bulb or whatever you want. You'll notice that there's no potential. It's zero. And that's what this is implying right now. So everything is balanced in it. But when unbalanced ionic charges are in it, that's when we have a potential. So how can we make that balanced, unbalanced? So what I'm going to do, let's see. So I happen to have brought with me a couple of things to demonstrate that potential. This is a depiction of a water molecule. I had a whole pocket full, but it kind of leaked out. So I got this one left here. This one water molecule representation has an oxygen atom and 2 hydrogen atoms, which is how water is composed. Is that right, Scott? Yep. Scott said, yeah, he knows because he's been rained on. So water is like this. Now, if you look at this, to the untrained eye, it's not apparent that this has any electric potential to it. But as a matter of fact, this is completely balanced because there is much positive charge showing this way as there is negative charge from these two, and as much positive charge showing this way as negative charge this way. So both in these directions, this is a balanced molecule. There is no difference. But now what if I did this? I went and compressed this. Now things are changing a little bit because you've got this displacement between this positive. He's now going down. There you go for the camera. Down, spreading these guys out. And now the electric potentials are offset. They're no longer in balance. And because of that, this becomes a polar molecule, meaning when I do this, this becomes more positive here and more negative here. So I've just converted this from a balance to an imbalance. Now, and which means, by the way, you can generate electricity from ice. Is that true, Rick? Did I just lie to you?
It's true.
He says it's true.
Yes.
I'm going to hold you to that. Okay, so this is a picture of a lattice of something else. What do you think it is, Adam?
Your guess is as good as mine.
My guess is that it's wood. Okay, plastic.
Sure.
Okay, sure. So I don't know what it is. I just made it up. But what it is, it's a completely balanced piece of thing that has no net charge anywhere. And if I try to compress it, it doesn't go anywhere. I might just break the model. No matter how I try to compress it, it doesn't get closer, you know, and things are always in balance. And I'll never get anything out of it. However, if I go to this little model, I took the liberty of taking a crystal, I think it's topaz. Doesn't it look like topaz to you? He says yes. So it is. So I took a piece of topaz molecule lattice structure that it's made of, and I looked at it and I said, my gosh, this is actually polar, but only if it's squished. So right now it's in complete balance. There's as much positive here as there is negative, and everything's just balanced all the way around, just like that. But if I take this same structure and I squished it, now I've got more positive one side than the other, and so forth. And this becomes, therefore, a polar molecule, and it has potential. That means I can take glass and generate electricity. Well, not glass, but quartz crystal, yes, I can. Let's see. Let's go back to the slideshow and see where the heck I am. Oh yeah, completely balanced, zero. Okay, so here I am, I squished the molecule, and it's no longer balanced. I'm actually producing some difference in electric field. Or I can pull it apart. It's pretty hard to pull this glass apart. But anyway, I tried. So as long as everything's balanced, there's no electric potential. But if I compress it or pull it apart, there is potential. So this is known as the piezoelectric effect. It goes in tight. So that just means, in layman's terms, that this effect comes from compression and elongation of a crystal molecule that actually produces a difference in electric potential. So to us laypersons, the relationship is this, and the E in this case stands for the electric field. Electric field is equal to that constant K, which is the compressor amount that your crystal can handle, times the stressor. And so that means you have lattice constant times the pressure that you put onto it. This is known as the stress tensor, there you go. So it means that the harder you press, the more electric potential is generated. So if I really crush it, I can create a greater potential. Is that right, Rick?
Yes, it is.
Absolutely. So that's right. So the more I compress it, well, let's take it a step further. Instead of just compressing it, what if I took a hammer and I struck it really hard? Will it do the same thing? He says yes. In fact, we're going to prove it. Right, Rick? Yep. So there we are. Now, all these toys. Let's go back to the slide. Let's see. Potential generated. Okay, to the physicist, it's this little weird thing here. So if you're a physicist, this is dear to your heart, not to mine. So this little diagram now is an animation that shows a compressed cylinder, and it's connected to a galvanometer. And the galvanometer simply shows plus voltage, minus voltage, a potential as a result of the compression of that cylinder. Hopefully this cylinder is a crystal of some sort. So what happens is pressure then results in a non-zero electric field, and the non-zero electric field results in a voltage. That's what we defined it as. And the release of the pressure results in a reverse voltage. So there we go. Reverse non-zero electric field results in negative voltage. It's a lot of mouthful. So like what Rick was talking about here, by the same thing, not only on this diagram, this is a diagram of a hammer striking that same thing, that same crystal. Instead of breaking it though, it's actually producing, if you see this diagram, you'll notice that there's a little bit of a lightning bolt right there. And the lightning bolt shows that there is a electric potential is generated on that crystal and is discharging on the thing that it's on. So between the crystal ends, it's discharging. So that's it. The hammer is actually doing that. So there you go. Even a sharp blow, big jump in voltage, typically around 20,000 volts. Yeah, pretty good stuff. Potential difference then results in electric discharge. All right. So Some crystal lattice examples, just so you know. All right, like quartz and topaz, agate. This one is quartz, by the way. I don't find these too much out in the open, you know. I always want to find these big honking gigantic quartz crystals. My wife finds the best ones. I don't know how she sees them. I just step on them. Ow. So agate, sapphire, ruby, those kind of things are examples of crystal lattice structures. Most metals, in fact, when they cool, they congeal, they solidify into lattice structures themselves. Salt, sugar, ice, like we talked about, also congeal into those lattice structures. I mentioned this particular salt called Rochelle salt, by the way. I point this one out because Rochelle salt is the world's most most piezoelectric substance there is that we know about. You can strike that thing, of course, it turns into just powder. But if you can get it to stay solid, it'll generate more electric potential per pressure than anything in the world that we know of. That's why I mention it, that's all. Semiconductors, ceramics, lead zirconite, very, very strong and inexpensive for producing that. Your bone can actually generate electricity. Is that right, Bob? Bob says, I don't know. See? But down deep, he does know, but he didn't want to admit it. He doesn't want to show how intelligent he really is. What do you think, Bruce?
If you strike my bones, it hurts. What hurts is frequency. Never mind.
Did you? Even your DNA, all right? So even your DNA is also a crystalline structure that we know. But the things that don't do that same kind of thing, don't produce a piezoelectric effect, sometimes the surprising things like glass, okay? Plastics do not. Even not all gems do the same thing. Obsidian, amber, they do not. That's surprising about amber too, because amber was the one thing that we used like 3000 BC to actually generate some static, right? But here we're saying now, when we strike it, it doesn't. What do you think, Rick?
I looked at piezoelectric, and it talked about the people 7,000 years ago. They had all these stones, and they shake them to produce light.
Ah, so they shook them to produce light.
Yeah.
Did you do that when you were in Scouts?
I might have.
You might have, yeah. I believe it. So good. All right, so now here are some things that we do call crystals that are not really crystal, just so you know. And so this slide shows a picture of some glassware we call crystal glassware. They're crystal because they have lead in it, and that's why it's called crystal. That is not truly crystalline. Here's another one. This is a watch whose repairman is probably taking off the glass, and it's called a crystal because it's just a name. It's not really crystal. So it's a name. Okay, Crystal Gale. Okay, this is a picture of her. She is not really a crystal. Okay, she might argue with you against that. Okay, that's right. She generates. Well, I think the voltage comes from friction, but okay. So Billy Crystal is another one. These are not true crystals, just so you know. You can actually grow your own crystals at home. Amazon sells kits like this you can buy. This is a picture of a box that has, crystals you can actually grow. It's kind of fun stuff. With the crystals that you grow, can you do the same thing here and generate electricity? I see no, I see yes, some going in circles. Okay, so yeah, you can, as long as you don't smash it too hard, right? Okay. So a lot of kits are available that you can get. Okay, how about dilithium crystals? Huh? Is that a real, true crystalline structure? Well, only in your dreams. Okay, so probably not. Okay, they kind of made that up, and it's kind of fun. We really like to talk about it. I don't know anything that's a true dilithium crystal, but I just wanted to get it out of the way in case you were thinking of it. And I know people like Rick, different Rick, was thinking about that. I could sense it from here. All right. Some applications for these are like applying pressure to generate voltage, barbecue igniters. In fact, I happen to have brought with me a barbecue igniter tonight. I stole it off of my mother's barbecue grill. She passed away, and I figured she wouldn't mind, but there it is. An igniter just like that. And inside here, It no longer works. No. Yeah, it used to be. Inside here, what you got is a spring-loaded plunger, and the spring-loaded plunger then will strike this crystal that's inside here, and on the end of the crystal is this piece of metal that is a conductor, and on the other end is this ground wire, and if I connect these two and then snap this, I should be able to start a fire in my barbecue. Is that right?
That's right.
Can you demonstrate that? So here's Rick demonstrating.
That feels pretty good. I like that.
He likes it. Okay. I recommend that every morning. I'm the doctor. You can tell because of my lab coat. Once a morning, you can do this. So anyway, let's see, barbecue igniters, guitar pickups, believe it or not, those things really are piezoelectric receptors, microphones. A lot of our microphones have, not all microphones, some of them are condenser, some of them are different. Like the microphones in your smartphones, those are piezoelectric. Ultrasound sensors, strain gauges, weight scales, automotive pressure sensors. Here's an interesting application for one in case you just are dying. So Rick just demonstrated that he was able to, you're not related to Dr. Frankenstein, are you? He is. And so that's why he got a good jolt out of that barbecue igniter, and he's still alive. Huh? So what I'm going to do is that very same thing, but instead of Rick, I'm going to do it on this fluorescent bulb right here. Is there a way to turn off these lights, or are they on forever?
When you're ready.
I am ready. So he's turning the lights off at this moment, and I'm going to try to see if I can light this up. You notice nothing up my sleeve, no batteries. I'm just going to use this guy here onto this fluorescent bulb. Did you see it? It's not very bright, okay? But there it is. There it went again. Let's see if maybe it's better down here. But you can see that it's lighting up a little bit. Sorry, Linda, Sabra, and Sylvia, you can't see it. Trust me, it lights up. You can ask Rick. Rick always tells the truth, right, Rick? See? So, don't lie to me. Okay, so yeah, when I do this, so what's happening? What's happening is that this crystal inside is actually generating that electric charge. Electric charge is hitting this tube, and it's actually conducting. So now we've got this electrical potential that's actually jumping inside this tube. I won't even get to how that happens. It's capacitance. Don't worry about that. Lights, please. Thank you, James. All right. So I've lit up my fluorescent bulb. This is a picture of me or somebody using that very electric igniter to light up that fluorescent bulb. All right. And so the process, like I mentioned, is reversible, and that means that you can actually apply voltage to actually compress the thing. So are you telling me that I can apply voltage to this big honking piece of glass and it'll compress the glass? Is that what that means? Jack says yes. I believe you're too slow, Rick. Jack beat you to it, and it is right. It will actually compress the glass. That is true. So things like your musical greeting cards, ever got one of those before? Open those things up, happy birthday to you, right? And those things are singing to you by that very thing, the crystal, the piezoelectric effect. Some of your earbuds have that, hearing aids do, inkjet printers use them, ultrasound transmitters, some the ultrasound cleaners. Sonar actually uses, this is one of the very first applications in modern times for the piezoelectric crystal, and that is for sonar, believe it or not. Okay, this is a simple diagram I'm showing here, a schematic of an oscillator circuit. So what I've done is I've taken that crystal and I've placed it in this circuit so that it's in parallel with the resistor and an inverter. And what the inverter does is it simply, when I'm applying a voltage in one direction, then it switches and it goes back and forth. And suddenly now, no longer is the crystal simply going, that it's going to generate one spark and goes away. Now it's going to go back and forth, and it'll eventually die off unless I keep applying voltage to it. And that energy, that voltage comes from the inverter. And so what the inverter does is it's always powered on. And so what happens is you got the crystal here that starts it going because you've got a little bit of current, and then once it goes, the inverter goes, oh, I'm going to switch it around, add more current, switch it around, add more, and it goes back and forth and back and forth. And next thing you know, the output of this thing is going to be an oscillating voltage. Here is a symbol of, this is a symbol of a crystal that we use in engineering. This is a little thing called a resonator. I'm not going to get into the details about the difference between a resonator and an oscillator. These little guys here are called CAN oscillators because they not only have a resonator inside, but just a crystal, they also have the resonator circuit that you saw just a second ago. So a whole circuit inside that actually keeps it going and powered. This kind of oscillator is what we used in everyday engineering to make sine waves and other interesting waves, square waves. But anyway, so there you go. This is a photo of some old-time crystals that we used to use in ham radio long time ago. And what we did was, instead of changing frequencies, we would pull out the crystal, put in another crystal, and suddenly we were vibrating with a different frequency. And that's what we did. And these radios are what we used to call rock bound because they're stuck by the rock, the crystal. So, and in fact, I brought a couple things here. I'm going to pass these around so you can see them. I'm not going to give it to Rick first because he's probably going to keep them. So I'll start with Bruce. Over here, you can kind of pass them around and see these. And what you'll notice is that these rock-bound crystals, that they only have two legs in them because they're just one side of each of the crystal. They have screws in the sides of the rocks. And what that means is you can actually take the screws out, take the crystal out, grind them down to change frequency, put them back in. Did they used to actually do that? You think that's... Rick isn't sure.
I got my novice license in '66. I was rock bound.
So,
I actually did that with a little bit of cleanser.
So you actually have, so you know about the cleanser. So Jack has actually done this. Rick, Jack's done this. Yeah, it is possible you can do that. It's kind of hard to reverse that, but yet it's possible. What do you think, Bruce?
You ever had a floor with a tube in your hand there? You can rub your feet on the carpet, have a tube in your hand, the inside tube, blow the works. Put his hand to a piece of metal, it'll flash.
That's true, it will. Good example of static electricity. All right, let's see. Okay, here's an old crystal. This one's just this one I don't mind losing, so I'm going to go ahead and show it to Rick. There you go. You can pass that around, let other people look at it too. You can take a look at this quartz crystal. You have to talk to my wife about it, and she's stronger than I am. All right. So let's see on the next slide here. This is the thing you guys have been waiting for. Noji, quit talking and tell us what this has to do with ham radio. Well, I kind of did here and there, but what's going on is that it provides a stable frequency reference. And when we used rock-bound transceivers a long time ago, that did the job for us, okay? But it's kind of awkward to have to switch frequencies by changing out. So people ended up with these boxes of crystals, and you swap them out. I want 703. No, I meant 704 megahertz. And you lose them, and you break them, and you step on them, your dog ate them. So, this happens to rock-bound radios. So we solved that partially by actually saying, you know what, we can do better than that. We can use digital circuitry by actually making my own frequency. So here, I still need one crystal that provided my frequency for me, and then after that, I can change the frequency by synthesizing it. I can create new frequencies by my circuitry now. So that's what we have today. So Rick, when you go down and you purchase your Baofeng, okay, inside your Baofeng radio, if you tear it open, you'll never get it together again. But that's beside the point. You'll find somewhere deep inside one of the circuits is a crystal, and only one. But next to that crystal was going to be a synthesizer. And I don't mean a musical one. You and I are old enough to know about musical synthesizers. Not as old as Bob, but still, And that synthesizer will generate all the frequencies you need. So when you start changing frequencies, it isn't trying to change new crystals inside there. It's simply synthesizing and selecting different stages so you can get your frequencies. That's how it does that.
I used a lot of strain gauges in my life. So they were made out of this piezoelectric crystal stuff.
Yes, yes, absolutely. Strain gauges are exactly what they do.
On like 5,000 ton press brake.
Oh, yeah, yeah. All right. We need another volunteer. Bob's a volunteer. You were just raise your hand.
I'll just raise my hand.
Yeah, yeah, sure.
It seems way back when there was some scientific equipment. The crystal oscillators weren't stable enough, and they put them in an oven.
Oh, yes.
So how come they're so stable in your baofeng?
Okay, I can answer that, but that's outside the scope of this course. So what's going on is that when you start an oscillation going, okay, then your circuit understands where that oscillation should be. And then you've got feedback circuitry that says, oh, you're a little off, come back here. Oh, you're a little off, come back here. And your feedback keeps going back and forth, and it keeps it right on within like a half a hertz. I mean, it's deadly accurate. Okay, you know, in the Kryptonian world, maybe it's not so accurate, but for our amateur radio use, half a hertz is pretty good. But that's what happens. And again, I won't get into any detail, but yes, you still have drift, you still have physical limitations. So you're absolutely right about that. That happens. But we have now circuitry that's really smart that can stabilize that really nicely. So should we go back to using LC oscillators? Well, the problem with that is that crystals keep it within a certain range. You go to LC, then you got this thing swinging by so much. It's like once it gets outside of a threshold, then their feedback circuitry can no longer function. You'll burn up your transistor, and there goes your radio, and your wife is mad at you for buying another radio. So that's how that goes. So short answer to a really good question. All right. I'm not sure how many slides I got left on this, but anyway, let's see. So the rest of this, even today's microelectronics, where do we have microelectronics today? Thank you. Just about everything. I mean, I can't even think of anything, I mean, here's Sabre. She brought her dog here, Cricket. Cricket's probably got an RFID inside of it, doesn't he? Doesn't she? An RFID? RFID? A radio frequency identification? A chip. Yeah.
Yes, she
Oh, thanks. I don't know the modern term. Yeah, so she's got one of those in it, okay? And those kinds of things, absolutely. See this little device right here? It's an old-fashioned device called a telephone. And this telephone has those in it, and several of them, as a matter of fact. But the vibration thing, when I talk into it, the microphone, the speaker, this is like all kinds of stuff. I can shock myself just by talking on my phone. But at any rate, so all kinds of microelectronics.
CPU clock even.
Oh my gosh. Yeah, your computer has to have a stable CPU clock. If it's off by even a few, anyway, you can get into big trouble. Yeah, that's all of my slides, I guess. But let's see. Do I have any more toys? I do, but you guys aren't deserving of seeing them. So anyway, there you go. That's the basics of how piezoelectricity works. And you can, just by getting a little bit of stress on this guy here, as you saw Rick demonstrate, actually, can you get hurt by this, Bruce? I mean, Bruce does so much barbecuing, so much grilling at home. He is an expert at these igniters, aren't you, Bruce? So he's going to demonstrate now.
Yeah.
It's not very strong, but there's electricity.
So he is so used to his...
No, you got to understand. I'm a descendant of Faraday.
Oh, okay.
Faraday. So, playing with electricity.
Doesn't even phase you,
Genetic.
right? Okay, all right. Yeah, it's totally generic. And as a matter of fact, I mean, your heart implant can even compare with this, right? So it's so strong. Do you think this thing can kickstart someone's heart? Maybe, I don't know. But you know what? So if anybody you want to try it afterwards, please, it's right up here. Don't touch it to your tongue. I'm looking at you, Rick. but it's right here if you want to check it out. Barbecue igniter. But it's very simple. And the simplicity is what we're talking about. Just because of a little crystal and because of that pressure you're putting on it to generate electricity.
That's exactly what I'm looking for when you take up daily, please.
All right.
You're on mic duty.
Mic open.
Big swing.
Daily.
Okay, so one question, is there, I've heard theory, is this the principle that they're theorizing when an earthquake occurs, that they see flashes of light?
I do not know. I'm not familiar with earthquakes and flashes of light.
I've heard rumors that in proximity to faults and whatnot, they think that, or that people have claimed that they've seen flashes of light, and with harder rock, particularly quartz, and with those, that may be the case. I was wondering if you had anything on that.
I don't know.
No, I'm not going down conspiracy. This is like science.
Thank goodness.
So one of the ways to demonstrate piezoelectric to a group of kids, anytime you need to do it in a dark room, is just take 2 pieces of milky quartz. Works the best for this, but you can just bang them together and you'll get that blue dot. And what Dalen was talking about, if you have a quartzite or quartz structure like we have along the Wasatch Front, under the right circumstances, you're putting a lot of pressure, you generate a tremendous amount of energy, and some of that can be a piezo effect. And so there's been anecdotal things. People say, I saw flashes. And so doing backwards, some geophysicists have suggested that they may be seeing some piezo effects. And the problem is there's so much energy being released in an earthquake, God knows what's happening. And God's busy shaking the earth anyway, so busy.
Well, thank you, Jerry. Appreciate that. I did not know that. Yes, it makes sense that all that pressure would generate a lot. So, thank you. Scott, what do you think?
Noji, thank you for the presentation. My question is this. If oscillators have gotten that good and provide us with a stable frequency for, let's say, keeping time, whether it's on our cell phone or
your quartz watch, right?
Or our watches or our laptop, for example. And bringing that again back to ham radio, when we do FT8, we are told that timing is very, very critical. Tenths of seconds can make a difference as to whether or not you communicate with the other party or not.
That's true. It has to be on internet time.
So why is it that our computers don't keep stable time, and we actually need a program to continuously sync the time on our computers with one another?
I have guesses, but I don't know for sure.
Okay.
This gentleman has an answer.
Okay. Thank you.
So it basically boils down to, we have good crystals. It boils down to cost. We can make crystals that are very, very accurate short term, but over time, even a few parts per billion, an oscillation every hour or so will stack up and you will drift over time, unless you're going to go absolutely crazy and build an atomic clock in your computer. So it's just accuracy. But also, now that you can have the most precise clock, an atomic clock, if it's not synchronized to someone else's clock, you're going to miss your timing windows, because FT8 is a time multiplex signal. You have to have your clocks agreeing with each other so you can each take your time slot. You don't step on each other. So that's why you have the network time protocol. You have NIST with their atomic clocks. They put them out that time signal on the internet. You can also get it from GPS. There's GPS disciplined oscillators where they have a quartz crystal, and it's clocking along. It gets a 1 pulse per second signal from GPS, which comes from an atomic clock up on there. And over time, they can say, oh, I was supposed to count, 10 million cycles, but I counted 10 million and one, and we've done that 1 second. Let me tweak that, a loop a little bit, and over time, you discipline that oscillator and nail it down. So yeah.
What's your name?
I'm Brent.
Reg?
Brent.
Brent.
Yep.
All right, Brent, thank you very much. Appreciate that.
Yes, there's also something called stratum concept, which is if we don't agree what the time is, it's like daylight savings time. Arizona doesn't play. And so, it's a different time in Arizona. You lose you gain an hour when you go to Las Vegas and you come back because we haven't agreed on time. And there's a new physics paper out that says, oh, by the way, time might not exist. So God knows what we don't know. But also you're banging on crystals. Whether you're banging on those crystals with a hammer, like Noji's demonstration, or you're banging on it with electrical energy. Energy's energy, and it doesn't get destroyed, it gets changed. And if any of you have ever been, stuck your finger in a light plug, you'll find that it gets changed, and it beats on you. And over time, things drift in your computer and everywhere else. So you have to agree on time. And so what's happening on FT8 is the Stratum 1 clocks are what the Stratum 2 clocks set themselves to. And so we have a number of Stratum 1 clocks that are all atomically based, and then a bunch of Stratum 2 clocks. And you get down to Stratum 4 or 5, and your network providers, major network providers, major telco providers, have very, very accurate clocks, as do the Stratum 2, 3, 4 that are used for GPS. And so in order not to step on each other, because we're talking about very fast signals, we have to agree on the time. And so you're setting your FT8 software to the same time that everybody else is using. But if you wanted to, theoretically, agree on a different time with somebody else you wanted to do FT8 with, you could make that happen, but you have to be agreed. And since you don't know who you're going to be making your QSO with, we agree that we're all going to use Zulu time that's very precise. And so we're grabbing
speaking
that
of
off the
agreeing
internet.
on time, we're getting close to the end of our discussion. So how much time we got left?
Oh, we've got time.
We got 1 minute, is what I just heard. I'm not going to stand up here any longer.
We were going to keep you a question over the next 3 days.
Thanks. Okay. Thank you, Bruce.
Everybody get a ticket?
For you, Rick, there is.
Somebody will show up to your house. No, may or may not be United.
Go ahead.
Am I the only one who didn't get to see what was being passed around?
Oh, I forgot to show you, sorry. Can you see the crystals and the...
I assume we kind of went around.
She's the one that didn't get.
Well, let's see. There's this one, and then there's
that's good.
that one.
Okay. Yeah. Okay. 2, 3. Do you want to call it out, or do you want me to?
You go ahead and call it out. I don't have my cheat.
Okay. I don't want to do him. All right, I'm going to call out call signs. We have 5 things at the end of the table there. And first come, first serve. We got AI7UG, KM7AIF, AB1IP, N7MFQ, and KK7AVS. Yes. Right there. Go get something off the table. On that end. On that end. Go for it, Gary.
And we also have 2 last year calendars, ham radio calendars. We'll sell them at half price. Or maybe we better give them away free. Anybody want them? First come, first serve.
Anybody want a calendar?
Going once, going twice. Sold. Yeah, they're good pictures. Yeah.
Annual events, when they took place last year, and they're usually on the same date or the same time frame the following year. Thanks.
Here, I'll walk us out. I got to do it all. All right, thank you again, Nochi, for presenting on piezoelectrics. Thank you, everyone, for attending. Just as a quick reminder, bookstore is always at all of our meetings. Field Day is coming up. Our next meeting is all about Field Day. Steak Fry is shortly after. All the information for both is on our website, utaharc.org. If you're interested in classes or you know somebody that is, please email James at kk7avs@gmail.com. Thank you. We're putting together a potential radio telescope program. If you're interested, email wj3ri@gmail.com. Okay, Brumman@xmission.com. Her information's in the microvolt. And we would really like to get the cow and the calf down into the valley. If you have some place to store 2 roughly 20-foot trailers, they are heavy, but we would really like to have them here in the valley for activities and fun. Thank you all for coming. Have a great night.